In mathematics, a quadratic form is a homogeneous polynomial of degree 2 in a number of variables. For example, is a quadratic form in the variables x and y. Quadratic forms occupy a central place in various branches of mathematics, including number theory, linear algebra, group theory, differential geometry, differential topology, and Lie theory. Introduction. Quadratic forms are homogeneous quadratic polynomials in n variables. In the cases of 1, 2, and 3 variables they are called unary, binary, and ternary and have the following explicit form, where a, f are the coefficients. Note that quadratic functions, such as x2 plus bx plus c in the one-variable case, are not quadratic forms, as they are typically not homogeneous. The theory of quadratic forms and methods used in their study depend in a large measure on the nature of the coefficients, which may be real or complex numbers, rational numbers, or integers. In linear algebra, analytic geometry, and in the majority of applications of quadratic forms, the coefficients are real or complex numbers. In the algebraic theory of quadratic forms, the coefficients are elements of a certain field. In the arithmetic theory of quadratic forms, the coefficients belong to a fixed commutative ring, frequently the integers z or the p-adic integers zp. Binary quadratic forms have been extensively studied in number theory, in particular, in the theory of quadratic fields, continued fractions, and modular forms. The theory of integral quadratic forms in n variables has important applications to algebraic topology. Using homogeneous coordinates, a non-zero quadratic form in n variables defines a dimensional quadric in the dimensional projective space. This is a basic construction in projective geometry. In this way one may visualize three-dimensional real quadratic forms as conic sections. A closely related notion with geometric overtones is a quadratic space, which is a pair, with V a vector space over a field K, and Q, Vk a quadratic form on V. An example is given by the three-dimensional Euclidean space and the square of the Euclidean norm expressing the distance between a point with coordinates and the origin. History. The study of particular quadratic forms. In particular, the question of whether a given integer can be the value of a quadratic form over the integers, dates back many centuries. One such case is Fermat's theorem on sums of two squares, which determines when an integer may be expressed in the form x2 plus y2, where x, y are integers. This problem is related to the problem of finding Pythagorean triples, which appeared in the 2nd millennium BC. In 628, the Indian mathematician Brahmagupta wrote Brahmasphata Siddhanta, which includes, among many other things, a study of equations of the form x2 minus ny2 equals c. In particular, he considered what is now called Paul's equation, x2 minus ny2 equals 1, and found a method for its solution. In Europe, this problem was studied by Brunker, Euler and Lagrange. In 1801 Gauss published Disquisitiones Arithmetici, a major portion of which was devoted to a complete theory of binary quadratic forms over the integers. Since then, the concept has been generalized, and the connections with quadratic number fields, the modular group, and other areas of mathematics have been further elucidated. Real quadratic forms. Any n times n real symmetric matrix A determines a quadratic form QA in n variables by the formula. Conversely, given a quadratic form in n variables, its coefficients can be arranged into an n times n symmetric matrix. One of the most important questions in the theory of quadratic forms is how much can one simplify a quadratic form Q by a homogeneous linear change of variables. A fundamental theorem due to Jacoby asserts that Q can be brought to a diagonal form so that the corresponding symmetric matrix is diagonal, and this is even possible to accomplish with a change of variables given by an orthogonal matrix. In this case the coefficients lambda 1, lambda 2, lambda n are in fact determined uniquely up to a permutation. If the change of variables is given by an invertible matrix, not necessarily orthogonal, then the coefficients lambda I can be made to be 0, 1, and -1. Sylvester's law of inertia states that the numbers of 1 and -1 are invariants of the quadratic form, in the sense that any other diagonalization will contain the same number of each. The signature of the quadratic form is the triple, where n0 is the number 0s and n plus or minus is the number of plus or minus 1s. Sylvester's law of inertia shows that this is a well-defined quantity attached to the quadratic form. The case when all lambda I have the same sign is especially important. In this case, the quadratic form is called positive definite or negative definite. If none of the terms are 0, then the form is called nondegenerate. This includes positive definite, negative definite, and indefinite. Equivalently, a nondegenerate quadratic form is one whose associated symmetric form is a nondegenerate bilinear form. A real vector space with an indefinite nondegenerate quadratic form of index is often denoted as Rp, Q, particularly in the physical theory of space-time. The discriminant of a quadratic form, concretely the class of the determinant of a representing matrix in K2, can also be defined, and for a real quadratic form is a cruder invariant than signature, taking values of only positive 0 or negative 0 corresponds to degenerate, while for a non-degenerate form it is the parity of the number of negative coefficients. These results are reformulated in a different way below. Let Q be a quadratic form defined on an n-dimensional real vector space. Let A be the matrix of the quadratic form Q in a given basis. This means that A is a symmetric n times n matrix such that where X is the column vector of coordinates of V in the chosen basis, under a change of basis, the column X is multiplied on the left by an n times n invertible matrix S, and the symmetric square matrix A is transformed into another symmetric square matrix B of the same size according to the formula. Any symmetric matrix A can be transformed into a diagonal matrix by a suitable choice of an orthogonal matrix S, and the diagonal entries of B are uniquely determined. This is Jacoby's theorem. If S is allowed to be any invertible matrix, then B can be made to have only 0, 1, and -1 on the diagonal, and the number of the entries of each type depends only on A. This is one of the formulations of Sylvester's law of inertia, and the numbers n plus and n minus are called the positive and negative indices of inertia, although their definition involved a choice of basis and consideration of the corresponding real symmetric matrix A. Sylvester's law of inertia means that they are invariants of the quadratic form Q. The quadratic form Q is positive definite if Q greater than 0 less than 0 for every non-zero vector V. When Q assumes both positive and negative values, Q is an indefinite quadratic form. The theorems of Jacoby and Sylvester show that any positive definite quadratic form in n variables can be brought to the sum of n squares by a suitable invertible linear transformation. Geometrically, there is only one positive definite real quadratic form of every dimension. Its isometry group is a compact orthogonal group O. This stands in contrast with the case of indefinite forms, when the corresponding group, the indefinite orthogonal group O, is non-compact. Further, the isometry groups of Q and -Q are the same O, but the associated Clifford algebras are different. Definitions. An NARY quadratic form over a field K is a homogeneous polynomial of degree 2 in n variables with coefficients in K. This formula may be rewritten using matrices. Let X be the column vector with components x1, xn and A equals B the n times n matrix over K whose entries are the coefficients of Q. Then two NARY quadratic forms phi and psi over K are equivalent if there exists a non-singular linear transformation CGL such that let us assume that the characteristic of K is different from 2. The coefficient matrix A of Q may be replaced by the symmetric matrix 2 with the same quadratic form, so it may be assumed from the outset that A is symmetric. Moreover, a symmetric matrix A is uniquely determined by the corresponding quadratic form. Under an equivalency, the symmetric matrix A of phi and the symmetric matrix B of psi are related as follows. The associated bilinear form of a quadratic form Q is defined by thus BQ as a symmetric bilinear form over K with matrix A. Conversely, any symmetric bilinear form B defines a quadratic form, and these two processes are the inverses of one another. As a consequence, over a field of characteristic not equal to 2, the theories of symmetric bilinear forms and of quadratic forms in n variables are essentially the same. Quadratic space is a quadratic form Q in n variables over K induces a map from the n-dimensional coordinate space knots into K. The map Q is a homogeneous function of degree 2, which means that it has the property that, for all are in K and B in V, when the characteristic of K is not 2, the map B, V times Vk defined below is bilinear over K. This bilinear form B is symmetric, i.e., B equals B for all x, y in V, and it determines to Q. Q equals B for all x in V, when the characteristic of K is 2, so that 2 is not a unit. It is still possible to use a quadratic form to define a symmetric bilinear form B equals Q minus Q minus Q. However, Q can no longer be recovered from this B in the same way, since B equals 0 for all x. Alternately, there always exists a bilinear form B, such that B equals Q. The pair consisting of a finite-dimensional vector space V over K and a quadratic map from V to K is called a quadratic space, and B is defined here as the associated symmetric bilinear form of Q. The notion of a quadratic space is a coordinate-free version of the notion of quadratic form. Sometimes, Q is also called a quadratic form. Two n-dimensional quadratic spaces are isometric if there exists an invertible linear transformation T, VV, such that the isometry classes of n-dimensional quadratic spaces over K correspond to the equivalence classes of NARY quadratic forms over K. Further definitions: two elements V and W of V are called orthogonal if B equals 0. The kernel of a bilinear form B consists of the elements that are orthogonal to every element of V. Q is non-singular if the kernel of its associated bilinear form is 0. If there exists a non-zero V in V such that Q equals 0, the quadratic form Q is isotropic, otherwise it is anisotropic. This terminology also applies to vectors and subspaces of a quadratic space. If the restriction of Q to a subspace U of E is identically 0, U is totally singular. The orthogonal group of a non-singular quadratic form Q is the group of the linear automorphisms of E that preserve Q, i.e., the group of isometries of into itself. Equivalence of forms. Every quadratic form Q in n variables over a field of characteristic not equal to 2 is equivalent to a diagonal form. Such a diagonal form is often denoted by classification of all quadratic forms up to equivalence, can thus be reduced to the case of diagonal forms. Geometric meaning. Using Cartesian coordinates in 3 dimensions, let be a symmetric 3×3 matrix. Then the geometric nature of the solution set of the equation depends on the eigenvalues of the matrix. If all eigenvalues are non-zero, then the solution set is an ellipsoid or a hyperboloid. If all the eigenvalues are positive, then it is an ellipsoid. If all the eigenvalues are negative, then it is an imaginary ellipsoid. If some eigenvalues are positive and some are negative, then it is a hyperboloid. If there exist one or more eigenvalues, then the shape depends on the corresponding If the corresponding, then the solution set is a paraboloid. If the corresponding, then the dimension degenerates and does not get into play, and the geometric meaning will be determined by other eigenvalues and other components if, when the solution set is a paraboloid, whether it is elliptic or hyperbolic is determined by whether all other non-zero eigenvalues are of the same sign. If they are, then it is elliptic, otherwise, it is hyperbolic. Integral quadratic forms. Quadratic forms over the ring of integers are called integral quadratic forms, whereas the corresponding modules are quadratic lattices. They play an important role in number theory and topology. An integral quadratic form has integer coefficients, such as x2 plus xy plus y2. Equivalently, given a lattice lambda in a vector space V, a quadratic form Q is integral with respect to lambda if and only if it is integer valued on lambda, meaning Qz if x, y lambda. This is the current use of the term. In the past it was sometimes used differently, as detailed below. Historical use. Historically there was some confusion and controversy over whether the notion of integral quadratic form should mean 2's in the quadratic form associated to a symmetric matrix with integer coefficients 2's out a polynomial with integer coefficients. This debate was due to the confusion of quadratic forms and symmetric bilinear forms, and 2's out is now the accepted convention. 2's in is instead the theory of integral symmetric bilinear forms. In 2's in, binary quadratic forms are of the form represented by the symmetric matrix. This is the convention Gauss uses in disquisitionous arithmetic. In 2's out, binary quadratic forms are of the form represented by the symmetric matrix. Several points of view mean that 2's out has been adopted as the standard convention. Those include better understanding of the two-adic theory of quadratic forms, the local source of the difficulty, the lattice point of view, which was generally adopted by the experts in the arithmetic of quadratic forms during the 1950s, the actual needs for integral quadratic form theory and topology for intersection theory, the Lie group and algebraic group aspects. Universal quadratic forms. An integral quadratic form whose image consists of all the positive integers is sometimes called universal. Lagrange's four-square theorem shows that is universal. Ramanujan generalized this to and found 54 multisets A, B, C, D that can each generate all positive integers, namely 1, 1, 1, D, 1, D7, 1, 1, 2, D. 2d14, 1, 1, 3, d, 3d6, 1, 2, 2, d, 2d7, 1, 2, 3, d, 3d10, 1, 2, 4, d, 4d14, 1, 2, 5, d. 6d10. There are also forms whose image consists of all but one of the positive integers. For example, 1, 2, 5, 5 has 15 as the exception. Recently, the 15 and 290 theorems have completely characterized universal integral quadratic forms. If all coefficients are integers, then it represents all positive integers if and only if it represents all integers up through 290. If it has an integral matrix, it represents all positive integers if and only if it represents all integers up through 15.